All right, good morning and welcome to Lounging Chemistry. So I had a couple of questions um, from a student today, and I'm just going to answer those questions. I'm just going to pull them up quickly. Right, so the first question was, what do subscripts in the formula of an ionic compound tell us about the arrangement of metals and non-metal ions? Right, so when you have an ionic formula, there's a couple of things to think about. So the ionic formula stuff starts here. Whenever we have an ionic formula, the metal is always written first and the non-metal is always written second. So if you have, say, for example, sodium chloride, sodium's the metal, it will be written first, and chlorine is the non-metal. When we think about the charges of each of these particular metals, we know that sodium is a +1 because it's going to be a group 1, or it is a group 1, right? So it will be a +1 ion. And we know that chlorine, being in group 7, will gain one more electron to fill up its outer shell. So it will be a -1 ion. +1 and -1 will neutralize each other out back to 0. So the ratio of the metal ions to the non-metal ions in this case is 1:1, right? We know, therefore, that the sodium chloride will be NaCl. When we have something like magnesium chloride, however, again, magnesium's written first because it's the metal. Chlorine is written as the second part of the equation because it's the non-metal. So the magnesium chloride, we look at where magnesium is on the periodic table. It's a 2 plus charge. It's in group 2. It's an alkaline earth metal. So it will be a 2 plus ion. When we look at the chlorine again, it is a 1 minus ion. So what we need to do to balance out that charge is we need 2 lots of these chlorines to balance the charge of the 2 plus, which is why we have the little 2 here. What I'm saying is that for every 1 magnesium atom, I have to have 2 chloride atoms to neutralize the charge of that, or for every magnesium ion, I need 2 chloride ions to charge that, right? And we can see the difference for those in the actual structures over here, right? For every sodium ion I have 1 chloride ion. And when they arrange themselves in this lattice here, they go 1 for 1, right? Whereas with something like, say, potassium oxide, where you have 2 potassium ions for every oxide ion, they are going to have a little bit of a different arrangement. The lattice will take on a different structure, and you see 2 potassium ions for every 1 oxide ion here. So it's 2 and 1, 2, or 2, 1, 2, 1, right? So it will take on a different arrangement. With the potassium oxide here as well, we know that potassium is a group 1, so it will be +1, and oxygen is a group 6, so we know the oxide ion is going to be O2 minus, which means that we need 2 of these potassiums to neutralize the charge of every oxide ion, which is why we have K2O. Something to be warned about, and I've put it down the bottom here in a different color, is when you see polyatomic ions. So the biggest indicator of these here is that you've got a magnesium, that's your metal, and then you've got a whole bunch of ions here, or atoms here, that are all non-metals. We know that nonmetals tend to covalently bond together with other nonmetals. So nitrogen here is covalently bonded to 3 other oxygen atoms. And we know, we should have a bracket here with a little 2. Because if I look at a polyatomic ion table, I know that nitrate is a 1 minus. So what I'm going to have to do, knowing that magnesium is a 2 plus, is I am going to have 2 of these nitrate ions, and the way that I'm going to do that is by putting a bracket around the entire nitrate group, because that entire thing is the ion, and putting a little 2 outside that bracket, which tells us that I have 2 lots of this group neutralizing out the charge of the magnesium. Right, so that was the first question. The second question, again, had to do with the structure of the particular lattices between a metal and between your ionic structure. So if we look at the differences, we have the metal over here with potassium. The potassium ions are all in a fixed position. In the case of your metal, we don't have a counter ion. What has happened is that the electron has left the ion and is now roaming delocalized around those potassium ions. It's kind of like an electron glue almost, sticking those ions together, right? The electrostatic attraction, which is the force that holds these things together, is between the positively charged ion and the negatively charged free roaming electron. Because the electrons are small, they can whiz and move in and around those metal ions, which means we get electrical conductivity. And when we hit that metal, some of these potassium ions can actually shift and the electrons will just move to compensate for that. So this is what makes these metals electrically able to conduct, and also it makes them malleable and ductile. We don't find that, however, with ionic solids. Ionic solids are not malleable or ductile. They're actually quite brittle. And it has to do with this structure here that we have. Because with this particular structure, there is also an electrostatic attraction. And it's very strong, right? But it's between now the sodium ion and the chloride ion in the arranged lattice, right? Because these chloride ions are big, they cannot move in and around. This is a fixed position. These atoms do not move. If I was to hit this part of those ions over, what we would see is the sodium line up with the sodium and the chloride line up with the chloride, and you would get repulsion and that would shatter, which is why these things are brittle, right? So the key thing to note is that they have strong electrostatic attractions between the positive ions and the negative ions, and that these things are always in a fixed position in the solid. Any other questions, let me know and I will help you out. But hopefully that answered your questions.